at this. You've done all kinds of stoich before. You've been stoiched out, if you want to put it that way. Chem 20, tons and tons of unit analysis and stoichiometry, big chunk of Chem 20. Our first unit, which was acids and bases, again, a lot of stoichiometry and unit analysis. And it comes back here. This is what we're doing. We're doing titrations. We're doing redox stoichiometry. The calculations, identical to what you were doing before. They do not change. Exactly the same. The only difference here is it's now based on a redox reaction, which is why we had to teach you how to balance that, because you got to have a balanced reaction, as we already know, to do stoichiometry. So we had to teach you how to balance these reactions so that we could do the analytical chemistry on them. So that's all we're seeing here. We will be doing a stoichiometry titration, a redox titration. So as I said, we've seen that we can perform titrations to determine the concentration of an acid or a base. And when we do that, essentially what we're doing is we react a known volume of some solution that we don't know the concentration of, and we react that known volume with another solution we call a standard that we do know the concentration of, exactly the concentration of, and we use that concentration and the volume obtained through the analysis to calculate the concentration of our unknown solution. So that's all I've said. We obtain the volume of the known solution for the titration. We use that value, the concentration of the solution, and the volume of the solution to calculate the concentration of the unknown solution. We can use this same technique to determine the concentration of other solutions besides acids and bases, and this is one that we're going to do that. The technique is used in redox. We also use it sometimes in water purifying. So, for example, the city of Calgary might do it to determine, using a precipitation reaction to determine heavy metal concentrations in water, in drinking water, and things like that. When we do it with the acid and base, we have to actually put an indicator in to know when the reaction is complete, because the acids and the bases produce a neutral ionic salt, and the neutral ionic salt is usually colorless. In many, many redox reactions, we're dealing with metallic ions that are changing oxidation state, and if we happen to have a metallic ion that's part of the transition metals, then those transition metals have different colors for the different oxidation states. So they self-indicate. So for example, chromium, if we look at our table, can be blue or green. So if it changes from blue to green, we know we've got the self-indicator there. Or manganese changes from deep purple to a pink color. So it self-indicates. Doesn't always happen that way. The reaction we will do when we do the lab on this, probably be next week, or maybe even later this week, the lab that we do, we're going to be titrating orange juice. So we're going to be titrating ascorbic acid with iodine. Now the iodine and the ascorbic acid does not. It's not one of the ones that self-indicates. So we have to put an indicator in there, but the indicator that we use is a starch solution. So when all of the I2 iodine reacts with the ascorbic acid in the orange juice, and the ascorbic acid's all gone, then the I2 will react with starch, and when it reacts with starch, it turns blue, or dark blue, almost purple. Okay? And so that gives us our indication of the end point. Okay? We'll talk more about that when we do the pre-lab for that lab. So technique is exactly the same. No different to what we did in the acids and bases. And as I said here, many times the color of reactant product are different in redox reactions. We can use that as a characteristic of titration. So our steps, though, same thing. Start with the balanced net reaction. Use any method that you like. So you can use a half reaction method or the oxidation number method, either one. But make sure, at least for your diploma, that you know how to assign oxidation numbers. I'm going to be giving you a quiz, and on that quiz, you will be forced to balance at least one reaction in both methods. Okay? But on the diploma, we leave it wide open. You can balance whatever method you like. That being said, you can't just say, okay, I don't need to know oxidation numbers. You have to be able to assign oxidation numbers. We specifically ask those types of questions. So we might give you a reaction and say, what's the oxidation state of manganese in the permanganate ion? And if you can't assign oxidation numbers, you're not going to be able to answer that question. So you got to know how to still assign them. You don't have to use them in balance. You have to know how to assign them. Step 2, calculate the number of moles of substance you know the concentration of. Step 3, calculate number of moles of the unknown substance, use your multimole ratio. And step 4, using the volume, calculate your concentration. So essentially, it's just set up your unit analysis. Okay? So with that in mind, let's have a look at his sample problems. In redox titration, 12.5 milliliters of acidified 0.8 mole per liter potassium dichromate was used to oxidize 100 milliliter solution of tin 2 to tin 4 ions. The volume of dichromate was just enough to oxidize all the tin 2 ions in the solution, meaning we hit endpoint, we stopped at that point. What is the tin 2 ion concentration in the solution? And what color change indicated the endpoint of this titration? So, our starting point is a balanced reaction, and so we know, and this I would not put it together like we've been using here. I wouldn't put this one together because these reactions are all in your data book. Don't forget what we've done in the past. You know, what's my redox reaction going to be? Well, I've got K2, so I've got potassium ions, I've got dichromate ions, it's acidified, so I've got hydrogen ions, I've got water, I've got tin 2 in there. So make that list. Find out what your OAs and your RAs are. Pick out your strongest OA, pick out your strongest RA. See if they're in the data table, because in this case they are. And then write your reactions from your data table, or from your data book. So realistically, you're not having to put anything together on your own. Use the data book half reactions. All you have to then do is balance the electron exchange, combine the reactions into your net reaction. So when we do that, what we get for a net reaction is this. 1 mole of dichromate, 14 moles of hydrogen, reacts with 3 moles of tin 2, making 2 moles of chromium 3 plus ions, 7 moles of water, and 3 moles of tin 4. Okay? Step 1 is to set up, and this is the way I've been doing it. I did it in the last unit, did it in this unit. Set up the units I want. So I want moles per liter of tin 2. So there's my moles of tin 2 on the top, liters of tin 2 on the bottom. But the moles of tin 2 drag along moles of dichromate along with it. So now I have to use the rest of these steps to cancel out all of these units. So next step is to cancel my moles of dichromate. So that's what I've done over here. And I've used my concentration to cancel moles of dichromate. So there's the moles of dichromate going to cancel. But the concentration drags along liters of dichromate. So, using the volume, I'm going to cancel my liters of dichromate. Top to bottom, they cancel. And because liters of dichromate are not a ratio type unit, so they don't have any other units on the bottom, they don't drag along anything on the bottom here, just a place value of 1. And so everything's canceled except the units I want. Moles over liters for tin 2. I can go ahead, do the math. I have 3 divided by 0.1 times 0.08 times 0.0125. 0.0125 is my 12.5 milliliters converted into liters. And get my final answer, 0.0300 mole per liter. So there's my concentration. Now, how do I know what the concentration of the, or what the color is going to be? If we go to our data book, and for redox, what you're looking for is at the very back on page 11 in your data book. Page 11, there is a color of common aqueous ions. And so what we want to do is we want to look up what is the color of dichromate, and then what is the color of tin, if it's there, what is the color of chromium 3, and what is the color of tin 4. Well, the tin 2 and the tin 4 are not in here. If they're not in this list, our assumption, at least at our level, is that they are colorless. So the tin 2 and tin 4 isn't going to help us. But the dichromate is here. Dichromate is orange as an ion. And the chromium 3 is green. So what are we going to get? Now it starts to get green at 0.01 and it goes to a blue-green by the time it gets to 1 mole per liter. So 0.03, we're looking at this going from orange as dichromate to green as chromium 3. When this solution turns green, we know we've hit the end point. This is a self-indicating reaction. You don't have to add anything special. Dichromate to chromium will indicate for us. And when there's no dichromate left, it won't be orange, it'll be green because of the chromium 3 plus. Any questions? If we're dealing with redox reactions, where we're looking at metallic ions, that chart is the one you're going to be looking at in most cases. It's got some polyatomic ions, some metallic ions there, but that's the chart that gives you the colors of some of these common ions that we use that have color on their own. Most ions have no color, they're colorless. But those ones there do have color. Okay, any questions? All right.